My name is Aiden Owen, and this is our design project for Team Finger Fixin' Good.
Hi everyone, I'm Lyndon, and I'm going to run you through our clinical problem for our design project. Osteoarthritis, also known as OA, and traumatic injuries commonly affect the finger joints, specifically the proximal interphalangeal pip joint, leading to cartilage degeneration, bone-on-bone contact, pain, stiffness, and loss of mobility. Individuals affected include patients with OA, rheumatoid arthritis, and those with severe finger injuries from occupational or sports-related trauma. Many patients undergoing conventional PIP joint replacement experience discomfort, a limited range of motion due to poor implant fit and lack of anatomical personalization. Finger injuries account for approximately 38% of the 3.5 million upper extremity injuries in the US, with the PIP joint being the most frequently injured finger joint. OA is a leading cause of joint degeneration worldwide, contributing to chronic pain, functional limitations, and reduced quality of life, especially in aging populations. Severe PIP joint degeneration is created with surgical joint replacement using silicone, metal, or pyrocarbon implants. Silicone implants risk instability and implant fracture. Metal implants can cause stiffness, loosening, and osteolysis. Pyrocarbon implants improve bone compatibility but require precise sizing and complex surgical techniques. Current standard implants lack customization, often resulting in suboptimal joint function and revision surgeries. Existing PIP joint implants fail to adequately restore natural joint motion due to poor anatomical fit and limited personalization. There's a critical need for patient-specific, anatomically accurate finger joint implants that improve mobility, comfort, and long-term outcomes while reducing complications and revision. Many patients, especially those with osteoarthritis who undergo conventional proximal interphalangeal PIP joint replacement surgery, experience a reduced range of motion and discomfort due to the incompatibility of the finger joint, which is caused by a lack of anatomical personalization and poor implant fit from current implant designs. As a result, patients face dissatisfaction, discomfort, suboptimal recovery, and the need for additional corrective procedures. The purpose of this design solution is to develop a personalized finger joint implant that improves anatomical fit and mobility, enhancing patient comfort and overall joint function while reducing the need for additional procedures. The objective of our study was to design a personalized PIP joint replacement that better matches the patient's anatomy and restores natural movement. Current implants often fail because they aren't personalized, leading to reduced mobility, discomfort, and the need for additional surgeries. To guide our design, we focused on several key research questions. First, we examined the main shortcomings of existing implant materials like silicone, metal, and pyrocarbon, specifically their issues with fit, fixation, cracking, or stress shielding. Next, we asked whether a 3D printed patient-specific design could address these problems by improving anatomical fit, stability, and durability. We also identified the mechanical performance requirements our joint must meet, including the compressive strength, fatigue life, elastic modulus, and range of motion to ensure it behaves similar to a natural PIP joint. Our hypothesis is that a personalized 3D printed implant designed to match the bone's mechanical properties will reduce complications, improve functional motion, and provide a more reliable long-term solution compared to current standard implants.
So we decided to go with compression testing rather than tensile or three-point bend because we determined that most of the force in the finger joint when bending or when having other forces act upon it will be compressive forces. And so the goal of our testing was to compare the compressive mechanical properties of our materials, so our PC and our ABS, by performing controlled compression tests on cylindrical versions of these materials using an Instron machine. And our independent variables in our testing were the material types, the Instron crosshead speed, as well as the specimen geometry. And our dependent variables, so our outputs, were compressive stress and strain response, modulus of elasticity, ultimate tensile strength, and fracture stress. And then we had two groups, our first group being the cylindrical samples of PC, and the second group being cylindrical samples of ABS. And these samples were tested. Each material was tested 3 times for a total of 6 tests. And we measured the specimen geometry, so the diameter and height of these cylinders, And then we referred to the ASTM standard to figure out the best rate for testing, which ended up being 1.3 millimeters per minute. So now moving into our compression test results, starting with the PC compression curves at the top, all three samples followed a pretty similar trend. They show a linear elastic region up to about zero point zero 0.05 strain, followed by a peak stress between 72 and 85 MPa. After reaching that ultimate stress, the curves level off, which indicates yielding and plastic deformation. Among the three, PC1 had the highest ultimate tensile strength at about 84.76 MPa, while PC2 had the lowest at about 71.94. Their modulus of elasticity ranged from about 1,208 to 1,299 MPa, showing fairly consistent stiffness across samples. Moving to the ABS results, overall stresses were noticeably lower compared to PC. The ABS curves reached maximum stresses between roughly 36 and 52 MPa. And ABS1 had the highest strength at 52.4 MPa, while ABS3 showed the lowest at 36.82. The modulus values for ABS range from about 1,084 to 1,152 MPa, confirming that ABS is less stiff and less resistant to deformation.
Hello, I'm Jackie, and I will be discussing our FEA testing and results. To test the performance of our prototype, we completed FEAs on both components of the joint replacement. And to run the simulation, we applied a force of 10 newtons to the head of each replacement and fixed the end of the side implanted in the bone. And from the simulation, we were able to learn that the head or cartilage replacement region successfully withstood the applied load. The summary and results table shows the values calculated during the FEA of the minimum safety factor, maximum stress, and maximum displacement. And while the minimum safety factor was very low in both replacements, this value is expected to increase after implantation, and the bone fills the gaps within the replacement.
Hi, my name is Kevin, and this slide covers our statistical comparison of compressive strength between PC and ABS. We tested 3 samples per material and calculated ultimate compressive strength. PC had a mean of 77.58 MPa with a standard deviation of 6.55, and ABS had a mean of 43.68 MPa with a standard deviation of 7.98 MPa. Now, to check whether that difference was statistically meaningful, we ran a 2-sample, two-tailed t-test, assuming equal variances. The variance assumption was reasonable since the standard deviations were similar with an SD ratio of about 1.22, which was less than 2. With n equals to 3 per group and df equals to 4, we obtained a p-value of 0.0047. Since this is below 0.05, we conclude the difference is significant at the 95% confidence level. So overall, PC shows a significantly higher compressive strength than ABS in our testing. And based on this result, PC is a stronger candidate to carry forward for the PIP replacement material.
In conclusion, from our testing, we found that PC outperformed ABS, showing significantly higher compressive strength and coming very close to our target requirement. Our FEA also highlighted areas of high stress and low safety factor, showing us where the design still needs to be improved. And these results support the idea that a personalized 3D printed PIP implant is feasible, but our study was limited by not being able to physically test the actual implant design and by using simplified biomechanics. So overall, our findings give us a strong starting point for improving the material selection and geometry in the future iterations.
And lastly, our future work, what we need to do to strengthen the design and make it more clinically relevant. First, we would evaluate additional biocompatible, bone-matched materials so our material choice is driven by both mechanical performance and implant safety. Second, we would test long-term fatigue behavior under repeated loading because the finger joint experiences thousands of cycles from everyday gripping and pinching, not just a single compressive event. Third, we would explore optimized 3D printed geometries and surface textures to improve strength and fixation at the bone implant interface. Fourth, we would use patient-specific imaging to validate fit and predict clinical performance using real anatomy rather than relying on generic geometry. And finally, we would benchmark our personalized implant directly against current commercial designs so we can quantify whether personalization actually improves strength, durability, and overall function.
Thank you for listening, and here are all of our references.